Hi, everybody. Welcome to Byte Ventures, where we deep dive into the marvels of technology. In today's case study, we'll discuss about Instagram's video compute efficient algorithm that saved their video compute time by almost 94%. So, without further ado, let's dive deep in. So, before talking about the problems and solutions, what the approach did they take, let's talk about a little bit of overview of what the things are. So as you know, Instagram is a very high scaled site. So they receive almost 2 billion monthly active users, for which they need optimizations to save on the server cost, video renderings, and all stuff. So whenever a video is uploaded to the website or to Instagram.com, then they create multiple encodings of the videos with different requirements. This is to help for efficiency and serve the right purpose. So the primary thing that they construct is a minimum functionality encoding, or which is called a lower compression and lower efficient compression, and the advanced encoding, which is called a new compression for high quality playback. So if you don't know about the difference is like the advanced encodings are sharper with lesser bit size. That means they can be smaller and even be crisper and more clear in the playback format. So, but that to happen, the device on which they are playing need to be new, because the device need to decode and play it on the client side. So that is pretty interesting. So what exactly was the problem in that case then? So the minimum functionality encoding that they had was taking up almost 80% of the resources, which was like a huge, because it took a lot of time for people to upload videos to the servers, and in some cases the upload failed as well. So the advanced encodings, which could produce or which required more compute time, would enable the users to see it more clearly without any fickliness or something, was only available to 15% of the total watch time, because of the lack of constraint of the resources, they were not able to compress using the advanced encoding methodologies. So let's dive a little bit deep into the minimum functionality encodings that they did. So the minimum functionality encoding did was having two major parts to it. The first part is the basic adaptive rate encoding, or basic ABR. ABR is a pretty standard terminology in video streaming services, and these consume some of the most watched videos. Like these consume the major part of the videos that Instagram had. So if you know about services like Netflix or YouTube, they use something called as the adaptive bitrate streaming. So that means whenever a user is trying to watch a video, the request first goes to the server to check what all possible resolutions are present for that particular video. For example, 240p, 360p, 720p, and so on. Based on the algorithms that they have, they compute the bandwidth that is available at the client side. If he's or she is present at a very high bandwidth thing, then they will probably load the 1080p resolution video. Or else, if they switch, because that happens dynamically. So for example, if you're watching the video at home with a high-speed internet connectivity, then you'll be probably seeing 1080p resolution of the video. But once you step out, you might see that the video suddenly blurs out, and in that case it is doing an adaptive bit rate streaming. So instead of pausing the video for loading that 1080p resolution, it switches to a lower resolution format for the user experience to be much better. So this is the pretty standard terminology. But the other thing was the progressive encoding, which was to maintain the compatibility with the older apps that don't support ABR. So this was not used much, but it was kind of like a legacy thing that they had to do, because to support the older devices or the older app clients. So they had to create both ABR and progressive from the original file. That means given the original upload from the user, it triggers two different encoding, which transcodes the whole thing into two different file formats as specified by Instagram. So the computations, or the time it takes, is almost around 86 seconds of CPU time to transcode a 23 seconds video into 720p. See how compute intensive it is, like almost 3x the time it's taking just to encode a video of that type. But with further analysis, they got to know that the ABR and the progressive are kind of very similar. So instead of having two different parallel structure going on, can't they do it sequentially? Like basically the output of one fed into the other is kind of the thing. So with the very minor differences in encoding profile and preset, they thought like, okay, this is achievable, and they planned the optimization in a very smart way. So this is the structure. So before this, they had the client upload the original file, which was kind of transcoded in two different versions. One is this, one is this. The progressive encoding was one structure and the ABR encoding was one structure, right? So this is kind of like happening both, and it was taking almost 86 seconds for a sample 23 seconds of video for a 720p resolution, right? So what was the optimization? They could figure out that, okay, these are kind of like very similar. So what they thought that, okay, taking one frame of the progressive encoding, they can repackage it to a format which is kind of supported through the ABR encoding, which is kind of like a huge revelation. They kind of saved a ton amount of resources, ton amount of compute by just doing this. Of course, they lagged some kind of efficiency because it's not done from the scratch, but it's kind of done on someone else. So it's kind of like a little trade-off on that sense, but they were quite okay with it because they could save huge amount of compute resources based on that. So just to give a context, it took around 0.36 seconds to generate a manifest file and repackage the video frames into an ABR capable file format for the same video. It was like huge success for that part. So now that they have done this, they wanted to test it out that, okay, whether this is working as expected or not in the production systems. Okay, so let's talk about how did they test it out. What could they use to test this whole thing out? So they built something as an experimentation framework where they routed the traffic across to two different kind of pools. So one of them is a test pool, one of them is a control pool. So it's kind of like based out of very similar infrastructure to compute performances. So basically what they did is like they replicated some kind of traffic through an experimented routing layer. So each request can either go to a test pool or a control pool, right? And the control pool will be running the current production services, basically the two things, that is progressive and ABR, happening differently. But the test is like a single linear chain that is happening. So it's basically the current code versus the code in production. You want to test out the performance. So once the image is generated or the video is generated out of this, they were tagged into different namespaces. The video that were encoded via test encodings were given or were uploaded to a different namespace, and the video that were generated by a control pool were put into a different namespace, just to make sure that the validation, the metrics are in the right place, right? So what did they observe? So they observed that the degrading, it was kind of a little bit degradation in the compression efficiency of the basic ABR. Of course, that would happen because instead of processing from the raw file, they're kind of doing it from the progressive frames, which was expected. But the major thing was the higher watch time for advanced encodings, because now that they have more compute resources, they can use this to increase the presence of more advanced encodings, and that would lead to more watch time for that kind of things, right? Awesome. So now they have tested and now they have validated their thesis that, okay, this is working. So now they need to push to production. Of course, they had to go through the CI/CD pipelines that Meta or Facebook or Instagram has. I'll not go into much more details, but these are kind of some of the metrics that they have. So once they pushed the code or the new code to production, they could see that the generation of basic ABR encoding went down by 94%. It was a huge success for that part. Because of a reduction in the basic compute for the ABR, because ABR was done almost every time, now they have more resource available. So more resource available led to more advanced encodings, and which led for the watch time coverage of advanced encodings increased by almost 33%. Huge success. And if you think about this, excuse me. So if you think about this, why they did focus a lot on the advanced encodings? This is because they were trying to scale out the services. So the people with slower connectivity will need to have these encodings for them to watch clearer and crisp videos, right? So that was their whole goal, and that they could achieve by optimizing the video encoding formats and all stuff. Awesome. That's all I had, guys, for today's case study. I have linked the official Facebook engineering blog in the description as well as on the top of this slide. If you have any question, just go through them or post in the comment section. I would love to answer those questions. Otherwise, see you on the next time. Thank you.